10.5 is on page 728. Talks about Euler and Hamilton paths. So we start with some reading. Can we travel along the edges of a graph, starting at a vertex and returning to the same vertex by traversing each edge of the graph exactly once? Similarly, can we travel along the edges of a graph, starting at a vertex and returning to it while visiting each vertex of the graph exactly once? Although these questions seem to be similar, the first question, which asks whether a graph has an Euler circuit. So what's an Euler circuit? Can be easily answered simply by examining the degree of the vertices of the graphs, while the second question, which asks whether the graph has a Hamilton circuit, is quite difficult to solve for most graphs. In this section, we will study these questions and discuss the difficulty of solving them. Although both questions have practical applications in many different areas, both arose in old puzzles. We will learn about the old puzzles as well as modern practical applications. So, if we're talking about an Euler path, basically, all what you have to do is traverse, so pass through each edge exactly once. And what is the difference between that and an Euler circuit? Well, it is passed through each edge exactly once, but starting and ending at the same vertex. That's the difference. So, we will learn about the town of Königsberg, Russia, now called whatever it is in the Russian Republic, was divided into 4 sections by branches of the, I'm not sure how to pronounce that, I'm guessing Pregel River. These 4 sections include the 2 regions on the banks of the Pregel Island and the region between the 2 branches of Pregel. In the 18th century, 7 bridges were connected these regions in figure 1, and here it is. So this right here is a flow of a river. This is all liquid. They build 1, 2, 3, 4, 5, 6, 7. This is the island. This is the land, 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 and land. So the townspeople took long walks through towns on Sunday. They wondered whether it was possible to start at the same location in the town, travel across all the bridges exactly once without crossing any bridge twice, and return to the same boat, to the same point. Basically, so a circuit is when you start and end at the same point. An Euler path is just going through the edges each one. So if you notice, this is land. This is land. There's 1, 2, 3 ways of reaching it. 1, 2, 3. This is the island. We call that A. It could be reached by 5 places. 1, 2, 3, 4, 5. 5 bridges. And this land B can be reached by 1, 2, 3. 1, 2, 3. And there it is. So, an Euler circuit is a graph. In a graph is a simple circuit. Circuit means it's closed. It begins and ends at the same point, containing every edge of G. An Euler path is a simple path containing every edge of G. So the difference between those, this is beginning and ending next at the same vertex. This is just going over the edges once. A connected multigraph with at least two vertices has an Euler circuit if and only if its vertices have an even degree. A connected multigraph has an Euler path, but not an Euler circuit if and only if it has exactly two vertices of odd degrees, exactly two. A simple path of G that passes through every vertex exactly once is called a Hamilton path. And a simple circuit in a graph that passes through every vertex exactly once is called a Hamilton circuit. Again, begin and end at the next same point. That's the difference between a circuit and a path. Path just going over every edge once. Circuit going every edge once, but beginning and ending at the same point. So if I look at the numbers 1 through 8, this is on page 739. It says, determine whether the given graph has an Euler circuit. Can you start at the same point and end at the same point? Construct such a circuit when one exists. If no Euler circuit exists, determine whether the graph has an Euler path. Again, circuit and path are the same, except circuit you start and end next to the same point. So let's see, 2, 4, 2, 4, 2, 4, 2, 4, and 4. So yes, a circuit exists. Why is that? Because we have all vertices having even degree. So if I want to start, let me see. I could go A to B to C, then go down F, I could go to H, G, and then I could go up to D. Now I could go, let me think really quick. I could go to E, and from E I could go to H, and from H I could go to F, and then F to E, E to B, and B back to D, and then D to A. There we go. That's one such path. So yes, I'm able to find it. How about number 4? Let's see. 4, 3, 4, 3, and 4. So here we have the degree of C and the degree of F are two odd vertices, so no circuit exists. But you could have a path since you have two odd, but you gotta start at one of the odds. Let's say you start at F. From F you go to A. A you run to B. B you run to C. C to E. E to F. Then to B. To D. BD. Let me think. To A, then from A all the way to E, E to D, and D back to C. So here, no circuit exists because I can start at the same point and end at the same point. Number 6, 2, 2, 6, 2, 6, 2, 4, this is 3, this is 3, so no circuit. If you recall, according to Euler's formula, they must all be even degrees. Oh boy. I'll get it right the third time. No. Oh, does that look wrong? Okay, no circuit exists, but a path could exist as long as you start at one of those. Let's say you start at B, and one path to C, to D, E, F, back to D, and now I'm going to go to G, then G I'll go to I will go to D, and D I will jump all the way to A I'll run to H runs to I goes to A goes to B, back down to I, and then terminate at C. We went every edge exactly once, but we didn't start and end at the same point. Number 8, 2, 4, 4, 1, 2, 3, 4, 2, 1, 2, 3, 4. So, okay, what do we notice? I notice on number 8, all the vertices are even, so we're going to say as an Euler circuit exists. And let's find such a path. This will be a long one. Let's go A, B, C, D, E, J. I could go to C, then come down to H, then run to I, that was almost that, then run to D, and back to B, come down to G. From G, let's go to M. From M, let's go to N. No, that's not working. From G, let's go to H. And from H, let's go to M. M to N. N will take us to O. Then we go from O to J. J to I run back down to N. Jump to L and wrap this up. M. Then go to F, to G, to M, to K, and back to A. And that one, back to F and then A. So a bit longer than tradition, but that's one path. You know, maybe I should write those down. I wrote them in my notes. So if I say A, A, B, C, F, I, H, then G, D, E, H, F, E, B, D, and A. All right. Okay. Number 4, no circuit exists, but I went over all of those, and how did I do? We started with F, then we went to A, B, C, D, E, F, B, D, A, E, and C. Also no circuit on number 8. This is really long. I'm not going to go Number 6 also is a bit long. I'm not going to list them out as I mentioned in the video. Now let's look at this bridge problem. So number 10, it says, can someone cross all the bridges shown in the map exactly once and return to the same vertex? Well, let's see. On number 10, can someone cross all the bridges shown in this example once and return to the starting point? So if I take this to be A, B, and let's take the islands to be C, D. So A, B, C, D. I could run 1, 2, 3, and from D I could run to A, and from D, that's it, and then from A I could run to B. So if I do the counting, 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, they're all even, so yes, I could do that in such a way. Let's see, if I start at A and I run to C, okay, that's too wide. Let me make this a bit further, just so that the highlight doesn't catch it. So A to C first, and then from C I could run to B and run all the way back to A, then to D, then to C, then back down. So I could have an Euler circuit. Start at A and end at A by tracing each edge exactly once. A to C to B to A to D to C, then to A. There we go. 18 through 20. So the fact that I have 3 right there tells me there's no circuit. 1, 2, 3, 4. 1, 2, 3, 4, 5. And I have 2 odds. There is an Euler path with no Euler circuit. So I have to start at one of those. Let's say one of the odds. So let's say I start at A and run to B. Then I run to D. Then I could go back to B. That's traced. Then from there I could go to C. Then from C to D and back. And then I could go from there to A. Then I could go to D. That works. So in that order. So it's A, B, D, B, then I went to C, then D, then C, then A. On number 20, so they're all even. Let me see. A circuit should exist. Euler circuit. So let's see. If I start at A, run to B, then from B I could run, I'm sorry, A to D, and from D I could run to B, and from D I could run B, come back, and then I could run to E, then from E run to B, back, 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 and back to the starting point. So that works. So how did this work? I went from A to D, then D to B, B back to D, D to E, E to B, back to E, and then I went to C, then to B, then to A. There we go. So we start and end the same. And 22, 4, 7, 5, 4, 6, this is, and 6. So I have two odds. Then a circuit does not exist, but a path would. I would start with the odd. It has to be one of the odds, C or B or C. So if I start at C, I'm going to end up at the other odd, which is B. So I could run from C, E, B, D, and then from D back to C. That part is done. And then I could go to B on one of those, and I could run to F maybe. Then from F I could go to D, and from there now I am bound to go back to E, and then I could go from there to F, back to E. That part is completely done. Then now let's run to A, run down from A down to F, then back, and at D, run to D, and take the middle. And there it is. This is a lot to list, but there it is. Now, Euler is going over every edge. Hamilton is going over every vertex, which is a bit tougher. Determine whether the given graph has a Hamilton. Well, no circuit exists because once I get to C to F, there's no coming back. So if I start at A, B, C, once I run to F, there's no way of going back to A and vice versa. So C and F are the issue. And here we have the same issue. If I look at this, the issue is E and F. If I start at F, there's no way of coming back. And if I start at E and I run to F, there's no way of coming back. So because of E and F, there's no way I could have a circuit. 36. If I go all around, so remember, you could go over an edge as many as you like, but you can only go over each vertex just once. Just once. There we go. That's one way of doing it. That's when we're doing it. 38. Does this have Hamilton path? Okay, Hamilton path go over every vertex, but not come back to the starting point. So if I run 1, 2, 3, 4, A, B, C, G, and E. It's asking if it has a path. This has a circuit. Okay, but it's asking if it has a path. It does have a path. Does 30 has a path? Okay, well here we know there's no circuit for sure. Because of E and C, D and F, there's multiple of those. And that prevents us from having a path as well. Because if I go in this direction, once I reach that, I'm stuck. There's no way of going back to cover this, and vice versa. So E, F, and G have degree 1. So once you get there, there's no way of continuing on to the next. So no path exists. And how about here? Well, let's see. I could run from, let me see, 1, 2, okay, I suppose there. I went over every vertex exactly once. No circuit, but a path. Let me see, can I have a circuit? No. So they're only asking for a path. And that's pretty much it for this section.